Start with the Milky Way. It is our home, and it is vast. A spinning disk of gas and dust spanning roughly 100,000 light-years across, holding around 400 billion individual stars. To genuinely understand that distance, imagine a single beam of light moving at the absolute maximum speed the universe allows. If you fired that beam from one edge of our galaxy, it wouldn't reach the opposite side for 100,000 years. When that photon started its journey, humans had not yet invented agriculture. And we aren't even the largest structure in our immediate neighborhood. Look toward the Andromeda galaxy, and you are seeing a system that spans 220,000 light-years and contains approximately 1 trillion stars. It outweighs us and outstretches us in every physical metric. Together, with about 80 other smaller galaxies, the Milky Way and Andromeda make up the local group. This entire gravitational family drifts through a volume of space roughly 10 million light-years wide. We treat these numbers as our baseline, the standard for what a massive structure should be. But looking deeper into the cosmos reveals anomalies that render our local definitions inadequate. Look over 1 billion light-years away, toward a dense collection of galaxies called the Abell 2029 cluster. Sitting at the exact gravitational center of this cluster is an object designated IC 1101. This diagram shows how IC 1101 maps against our immediate neighbors. The visible stellar body is 4 to 6 times wider than the Milky Way. But beyond that core, a diffuse halo of ancient stars stretches the galaxy's total diameter to roughly 4 million light-years. This chart compares the populations directly. The Milky Way holds about 400 billion stars. IC 1101 contains 100 trillion. That is 500 times the star count of our entire galaxy, held within a single gravitational structure. Placing IC 1101 at our coordinates reveals its true extent. Its stellar envelope reaches past the Milky Way and Andromeda, swallowing nearly the entire local group. A single galaxy occupies the same volume as our entire neighborhood. Astronomers classify IC 1101 as a supergiant diffuse galaxy, or a CD galaxy. These rare objects form exclusively in one environment, the absolute bottom of a rich galaxy cluster's gravitational well. They occupy the exact point where everything in the surrounding region is slowly falling. Because it sits at the bottom of this well, IC 1101 is subjected to a relentless process called galactic cannibalism. Over billions of years, smaller galaxies spiraling through the cluster lose their orbital momentum. Through a mechanism known as dynamical friction, they sink inward toward the center. When they arrive, the central giant absorbs them. This is not a peaceful merging. Immense tidal forces rip the incoming galaxies apart. Their structures are destroyed, their gas is swallowed, and their outer stars are stretched into distorted shapes, eventually pulled into long trails that mix into the growing body of the predator. This constant, violent merging heated and expelled all the raw gas needed to forge new stars. As a result, IC 1101 has no glowing stellar nurseries or brilliant blue stars. It radiates only the steady, fading yellow and red light of ancient metal-rich stars that formed in other galaxies billions of years ago. The starlight we see here is inherited. IC 1101 is a cosmic graveyard, assembled piece by piece from the wreckage of thousands of independent galaxies that wandered too close to the center over the last 10 billion years. Deep inside this massive accumulation of stars, astronomers found a physical anomaly. Despite absorbing so much material, the dead center of IC 1101 is hollowed out. It possesses a scoured, depleted core measuring roughly 14,000 light-years across. This massive cavity is the result of a process called core scouring. Every time IC 1101 consumed a major galaxy, that victim's supermassive black hole sank into the center. These black holes would then pair up with the existing central engine, spiraling toward each other to form a tight, gravitationally bound binary system. These orbiting supermassive binaries act like gravitational slingshots. Any star in the dense central region that wanders too close to the pair is violently ejected. Through a physical interaction called three-body scattering, The stars are accelerated to immense velocities and thrown entirely out of the core. Over billions of years, with dozens of supermassive black holes merging, this slingshot effect excavated an enormous amount of material. The estimated mass deficit, the amount of stars thrown away from the center of IC 1101, is roughly 490 billion solar masses. That means they ejected more stellar mass than exists in the entirety of the Milky Way. Those billions of exiled stars didn't vanish. They were scattered outward, settling into the sparse outer reaches of the galaxy. That colossal 4 million light-year halo is the scar tissue of a billion years of gravitational tantrums, built from the debris of the galaxy's own internal violence. We know that in roughly 4 to 5 billion years, the Milky Way and Andromeda will fall into each other. They will collide, destroy each other's spiral arms, and merge into a single massive elliptical galaxy astronomers call Milky Way. For us, this represents the final form of our galactic home. But if Milky Way were to drift into the Able 2029 cluster, that final form would simply be the next meal. It would add barely 1% to IC 1101's total mass. Everything we are and everything our local group will ever become would be shredded, absorbed, and scattered in that golden envelope. If you were to travel past those dying stars, piercing through the million light-year halo, you would eventually reach that scoured, empty core, a 14,000 light-year sphere of absolute darkness, cleared of matter by billions of years of orbital ejections. Sitting in the center of that darkness is the gravitational anchor holding this entire graveyard together. An overmassive black hole with an estimated weight between 40 billion and 100 billion times the mass of our Sun. A single object with an event horizon wider than our entire solar system. We know these engines exist. We have seen them. This is the supermassive black hole at the center of the Messier 87 galaxy, captured by the Event Horizon Telescope. That black hole weighs 6.5 billion solar masses. The engine driving IC 1101 is estimated to be up to 15 times heavier. IC 1101 is a monument to what the universe builds when gravity has 10 billion years, an unlimited supply of material, and absolute patience. It is the inevitable end state of cosmic structure, waiting at the bottom of the well. If we measure cosmic size purely by starlight, the upper limit of the universe appears to be IC 1101. It is a massive, slowly dying graveyard of stars, with a halo stretching across 4 million light-years. But that perceived ceiling relies on a human limitation. For centuries, we mapped the cosmos using only the narrow band of the electromagnetic spectrum our eyes evolved to process, visible light. Relying strictly on starlight leaves us blind to the largest structures in the universe. The most massive coherent objects in existence do not glow in the wavelengths we associate with suns or gas clouds. To find them, astronomers had to tune their instruments to radio waves, frequencies far below what any human eye can see. Through these radio lenses, the massive scale of IC 1101 is no longer the end of the story. It becomes the starting point for a different class of giant. The true scale of the universe's largest galaxies is invisible to us, forcing us to abandon starlight as our ultimate measure of size. This hidden scale begins with a cosmic engine, supermassive black holes sitting at the center of galaxies that often look completely ordinary. As these black holes feed, they fire tightly collimated jets of relativistic plasma into the void at nearly the speed of light. These jets punch through the surrounding stars and gas, slowing down as they hit the intergalactic medium to inflate colossal radio lobes of magnetized plasma. In 2022, astronomers discovered Alcyonus. Its host galaxy is unremarkable, roughly double the Milky Way's mass, but its output is staggering. The radio lobes of Alcyonus span 16 million light-years from end to end. You would need to line up 100 Milky Way galaxies just to match the width of this single radio structure. This proves that extreme cosmic reach is driven by the environment. The vacuum of the cosmic filaments allows these lobes to expand with almost no resistance. Even that record was temporary. In 2024, a new discovery pushed the limits of our understanding even further. This is Porphyrion, a giant radio galaxy with jets that span 23 million light-years. Porphyrion generated this outflow when the universe was less than half its current age. 23 million light-years is so vast that these jets stretch across 2/3 of the radius of an entire cosmic void. At this scale, the galaxy is no longer just moving local gas. It is physically touching the large-scale structural scaffolding of the universe itself. Porphyrion shows that a single black hole's influence can bridge the massive empty gaps between cosmic filaments. Structures like Porphyrion break our understanding of a galaxy as a contained, bounded object. We used to view galaxies as isolated islands floating in a mostly empty, inert universe. But as these giant radio jets reach across the deep universe, they actively inject energy, heat, and magnetic fields into the spaces between galaxies. This explains a major cosmic mystery: how the dark spaces between filaments became magnetized in the first place. We now know that these central supermassive black holes are the actual engines magnetizing the cosmos on the largest scales imaginable. And with thousands of these giant jet pairs already identified, we see this as a routine part of how the universe is built. If we view the cosmos not as a collection of stars, but as an interconnected network, the role of the galaxy changes. The universe is not merely a container holding galaxies. Galaxies are the active engines that build and architect it.